Okay, we talked about the two different types of substitution mechanisms, SN2 and SN1, and we went through the different details involved in each, the different things that prefer each different type of mechanism. So can we collate all that information, put it together, and answer a slightly higher order question, which is, given a particular substrate and nucleophile, can we figure out which mechanism the substitution reaction proceeds by, and if we can, what do the products look like? So we're going to see if we can do that. We got two reactions here, we got two reactions here. We're going to go through all four of them and we're going to see if we can figure this out. Okay? So let's look at this first reaction here. The most important thing to look at when you're figuring out which mechanism does your reaction proceed by is the identity of the substrate. And when I say identity, I mean, is it tertiary, is it secondary, or is it primary? We'd said before that tertiary substrates prefer the SN1 reaction. In fact, tertiary substrates proceed by SN1. Primary substrates cannot proceed by SN1 at all, they proceed exclusively by SN2. The grey area here is when we have secondary, which could potentially proceed either way. So in some of these questions it's going to be pretty easy to tell which mechanism you're going to proceed by because your substrate's going to be able to tell you. So let's look at these two. This guy here, 1, 2, 3, 4, 5, 6. We got 6 carbons. This is hexane. This is 3-methylhexane, 3-bromo, 3-methylhexane. Whatever the stereochemistry may be, it's either R or S here. The important thing to figure out though is this halide tertiary, secondary, or primary? And I'm sure you guys can tell that this is tertiary. Okay? Meaning this is going to proceed via an SN1 reaction. Now from what we saw before, SN1 reactions are also favored by weak nucleophiles, and well, it's not a surprise we have a weak nucleophile here as well. So hopefully we can figure out what our product or products are going to be. If you remember, if this is an SN1 reaction, what do you guys remember about how many products we're going to get? Well, we're going to get 2 products. And I'm going to draw out the products here after our final proton transfer. We're going to get out 2 alcohols. I'm going to draw out the stereocenters for each of our 2 products, just like so. If you remember, in the SN1 reaction we have scrambling of stereochemistry, so we get 2 enantiomers formed. One where the nucleophile has added in the same direction that the leaving group was originally in. And then we've got this guy here. And then in the other case we have where the nucleophile has added in on the opposite side to where the leaving group was, and we get that. And if you look at the stereochemistries of these, you'll see they are opposite of each other. Okay? But the important point is that we get 2 enantiomeric products because this is an SN1 reaction, and we tell that from the fact we had a tertiary substrate here. That's all we needed to know. Then when we look at the reaction down at the bottom here, you can see this reaction, or this substrate, is definitely not tertiary. There's only one group coming off the carbon with the leaving group. This must be primary. Primary substrates only proceed via SN2 reaction, which an SN2 reaction also dictates it prefers a strong nucleophile, which is what we have here. We also have a polar A product solvent. Now, we'd said that in the SN2 reaction, it proceeds with inversion of stereochemistry. So if this was S, we'd go to R. However, in some cases, you'll see a substrate where there's no stereochemistry shown. The important thing to understand is, if there's no stereochemistry shown in the starter material, you can't show any in the product either. Provided, though, you can understand that the nucleophile comes in to that carbon and kicks out the chlorine, and then you draw out the product where we've got this here. Alright, actually, you know what, I should leave a little bit of a gap there, where you show this So you've got your 3 carbons, you have your nucleophile that's now added in, and then you have your leaving group, like so. It doesn't really matter whether you show this leaving group or not, as far as I'm concerned. The important product is this one. There is no stereochemistry to show here because there was none in the starting material. Okay. So can you guys see predicting SN2 versus SN1 reactivity is pretty simple if your substrates are tertiary or primary. The issue comes in when we have secondary, and that's what we're going to look at here. We take a look at this substrate here. The leaving group, yes, it's not a halide, but it's still a good leaving group. NH3 plus is going to come off as ammonia, which is a weak base because it's neutral. This is a good leaving group, this is a good leaving group. In fact, it's exactly the same thing. Look at the carbon with the leaving group. There's 2 carbons either side of it. Both of these substrates are secondary, meaning they could occur, the reactions could occur by either SN1 or SN2. So if you can't tell from the substrate, you've got to go on to something else, and that something else next up is the nucleophile. We have to decide. If the substrate won't tell us what reaction we're proceeding by, the nucleophile will. We usually don't need to look at the solvent to tell which mechanism we are proceeding by. The nucleophile is going to be enough here. So take a look at the 2 nucleophiles. They look quite similar. Obviously they're not exactly the same thing. We've got hydroxide and we've got water. We know hydroxide's a strong nucleophile because it's got the negative charge there. Therefore, that would imply an SN2 mechanism. Water, on the other hand, is weak, which would imply an SN1 mechanism. So let's draw out the products, okay? For an SN2 reaction, how many products would we expect it to get? Well, of course, we'd be expected to get 1. And if you remember, there's particular stereochemical outcomes of an SN2 reaction, which is inversion of stereochemistry. In other words, the nucleophile comes in from the opposite side of where the leaving group was, meaning like so. Now I realize that I've drawn something here that's not actually chiral. That's kind of my bad. But the point is, if this is on a wedge, this is going to be on a dash. All right. And you know what? I should probably make a little bit of a change here. I'm going to add a methyl group here just to make sure that this actually is chiral, because otherwise we'd run into some problems in this SN1 reaction. So this is chiral, so this is a stereocenter here. So if the leaving group's on the wedge, the nucleophile goes in on the dash. And again, as before, I don't really care whether you show the leaving group, that doesn't really matter. What matters is this group here, with the opposite stereochemistry to what you had before. If we just check here, the NH3 is priority 1, this carbon is priority 2, this carbon is priority 3, so this stereochemistry would be R, implying that this stereochemistry would be S. Okay. Now I'm going to draw the hydrogen on here because we got to show that it's on a wedge, because here it was on the dash. We know it's priority 4 there. The alcohol is priority 1, the hydrogen's priority 4. Because of this extra methyl, this carbon's priority 2, and this one is priority 3. So we go around clockwise, which looks like it's R, but because the hydrogen is pointing towards us, it's S. So just as we said previously, in the SN2 reaction, the stereochemistry gets inverted or flipped. R here and S here. For the SN1 reaction, though, we'd said that the first thing that happens is that the leaving group comes off, basically because the nucleophile is not strong enough to get in yet. Leaving group comes off and the nucleophile can add from both sides. And so what we get out, now I didn't mean to draw this in red, but oh well. What we get is the fact we have 2 products that are only differentiated by the position at which the leaving group came in, the nucleophile came in. There's going to be 1 product where the nucleophile comes in, and I'm showing the product here after our proton transfer. We have 1 product where the nucleophile comes in on the wedge, and then we have the other product where the nucleophile comes in on the dash. These are enantiomeric products. They're present in a 1-to-1 ratio. If you remember, this is a racemic mixture. If you look at the stereochemistry here, it's the same as it was up here. This is R, meaning this guy is R and this is S. So our stereochemistry is mixed here. Alright. So the thing to remember is whenever you do an SN2 reaction, you always get out one carbon containing product. The SN1 reaction always produces two products. It's kind of a hallmark of the SN1 reaction, which is two products. SN2 is one product. Just as before here, SN2 gives you one product, and the SN1 reaction gives you two. So that's how you can predict products of substitution reactions, whether they are proceeding via SN2 or SN1. The key is tertiary substrates proceed exclusively via SN1, primary substrates proceed exclusively by SN2, secondary substrates proceed by either, depending on the nucleophile.